Hi and welcome to the week 6 video, the second video for the week, exponential and logarithmic functions. So as we go through this video, there's a lot of it is just going to be writing down laws and properties. So what you see on the screen, make sure you put in your books. We're going to refer to them quite a bit. First one is the exponential equations property. If a to the power of m equals a to the power of n, then m equals n. That's fairly straightforward. Looking at an example of that, if 3x equals 81, we want to solve for x, then we can rewrite 81 as 3 to the power of 4. As the work we're doing now, knowing some of these basic exponential or power values is going to be really handy. So knowing 81 is 3 to the power of 4, knowing 64 is 2 to the power of 6, things like that is going to be really useful to know. So if 3x equals 3 to the power of 4, then obviously x equals 4. These are index laws. You've seen them since grade 9. Pause the video now, write them in your books. We're going to refer to them shortly. I won't go through them. The index properties, again, you should be familiar with them. Pause the video, put them into your books. So we're going to take those properties and rules and use them to apply them to solve equations. So we've got 3 equations we're going to look at. The first is 25 to the power of x equals 125 to the power of 3x minus 1. Now 25x, we can rewrite 25 as 5 squared. So that equals 5 to the power of 2x. So we're just using our index laws there. We multiply the indexes together. So we get 5 equals 25x equals 5 to the power of 2x. Likewise with 125, that should be 125 to the power of 3x minus 1. 125 is 5 cubed. So again, using our index laws, we can rewrite that as 5 to the power of 9x minus 3. Now, if those are the same base, the indexes must equal each other. So we have 2x equals 9x minus 3. We solve for x equals 3 over 7. Now, with these answers, we can always verify them by substituting them back into the initial equations. So 25 to the power of 3 over 7 is approximately 3.97. And likewise, if we substitute 3 over 7 to x, we have 125 to the power of 9 sevenths minus 1, which is 3.97. So I can be fairly confident that I've got that answer. I've solved that correctly. Always verify your answers, especially in exams. The second one is fairly similar to what we just looked at. Again, identifying that 81 can also be rewritten as 3 to the power of 4. Now we chose the base 3 because we have a base 3 over this side. This left-hand side can't be taken down any further. So we break down that right-hand side to have a base 3 as well, which comes out to be 3 to the power of 4 brackets 3x plus 1. So because we have the same base, the indexes must equal each other. Again, solving for x gives us negative 1/7, and we verify our answer by putting negative 1/7 into our original value. Now as you're going through these examples, just step through them, understand why we're making the jumps we are, and what laws and rules we're using, and just make sure you understand the flow of it. If not, we're going to get a lot of practice over the next few weeks of solving these anyway. So we verify our answer, it comes out correct. The last one is probably a little bit more difficult than the other two, but if we just break it down and realize that this isn't as straightforward as the previous ones. We've got a plus 8 here, 6 times 2 to the power of x. We can't break that down any further. So if we bring the 6 times 2x over the other side, over the left hand side of the equation, and make it equal to 0. The key to this type of question is identifying that 2 to the power of 2x can be rewritten as 2x brackets squared. So this is kind of the reverse of what we previously looked at. We're just taking the 2x now and breaking that into x and squared. So here we've got 2x squared, 2x bracket squared minus 6 times 2x plus 8. We can substitute u for 2x. Okay, so all we've done is put in the brackets, we've let equal to u because those are the same values. It comes out to be a quadratic. And then we can just solve that as any other quadratic. So we get u equals 2 or u equals 4. And then using both of those values, we can solve for x. So we get x equals 1 and x equals 2. And obviously if we wanted to verify our answer, we would put it in here. We'll look at logs now. Logs are the inverse of exponentials. And again, we're going to go through the rules and the properties, so you can pause the video, write them down in your book, and we'll look at some problems and solve them shortly. But if a to the power of m equals x, then we can rewrite that as m equals log to base a x. For example, 10 squared equals 100, so that can, if we write that as a log, the index 2 equals log base 10 100. So in your calculator, if you put log 100, you will get 2. The calculator's default to base 10. So these are our log laws. Press pause, write them in your book. Similar to the index laws, if they're multiplied, we add them. If they're dividing, we subtract them. This third law is very important and we use it quite regularly. The log base a x to the power of n, the n comes out in front of the log and we're just left at log base a x. We'll use that quite a bit. And again, these are properties. Pause, write them down. We're going to use them now as we look at solving some log equations. So we're going to look at 3 log equations. The first one, we want 1000, x equals to 81. We want to work out what x equals to. Now, we know, which hopefully we all know, 1000 is 10 to the power of 3. So we can write 1000x as x to the power of 3x. Oh, sorry, 10 to the power of 3x. So we're left with 10 to the power of 3x equals 81. And we're going to use this rule here. So just rearranging that using logs. So our index 3x equals log base 10, 81. Now this is just a number. We can use it, get it from our calculator. So to find x, we put log 81 into our calculator, divide by 3, and we get 0.636. Again, we can verify our answer by substituting that 0.636 into our initial equation. So 1000 to the power of 0.636 is 81, or 80.91. Allowing for the rounding that's taken part here, that's close enough. The second one, we are adding 2 indexes together, or 2 logs together. So if we're logging them together, we can write them as a single log if we multiply the values. So we can rewrite log base 2 4 plus log base 2 16 as log base 2 64. Now we actually want to get a value that equals something. So we need to take it a bit further than that. So if we recognize that 64 is 2 to the power of 6, we can rewrite that as log base 2 2 to the power of 6, and then using this third law that we looked at, the index can come out the front, and we just have log base 2, and using this property here, log base a of a equals 1, that log log base 2 equals 1, so we have 6 times 1, which equals 6. In the third example, we're going to look at 6 to the power of x minus 2 to the power of x plus 2 equals 0. We can start by putting those equal to each other. So we've got 6x equals 2x plus 2. Now if we take the log of both sides, and what we do to one side we can do the other, these rules still apply here. So all we've done is taken the log of both sides, and if we use this rule here, x become log base 10 6x becomes x log base 10 6. Again, this log base 10 6 is just a number, and we do the same on the right hand side. So we have x plus 2 log base 10 2. So here we expanded that out, so x times 10 base 2 plus 2 log base 10 2. We can take or group the x's together. So if we bring this x value over to the left hand side, we have x brackets log base 10 6 minus log base 10 2 equals 2 log base 10 2. So we can work out that as anywhere there is a log, these are just numbers, so we can put those into our calculators. And with our calculators, they are log base 10. So if we have it in log base 10, we can just put them into our calculators. So then we can get x equals 1.26. And we will verify that answer by putting it back into our original equation, and we get approximately equal to 0, given that we did a bit of rounding here. Okay, so those are an introduction to the log and exponential functions, the rules and the properties that we can use to solve those equations. What we need to do now is just to take those rules and properties and continue to apply them in different situations so that we become confident in our problem solving abilities.